I'm Charles Pooh, and I work for Wolfram Research in algorithm R&D, and I will be talking about the new feature in version 12 in geometry. I'm going to talk about what's new in geometry in version 12, or the coming version. Well, I will try to kind of condense it. There have been a lot of change, a lot of improvement throughout the whole framework of geometry. So I will just try to show you what you can probably notice. So I will talk about the improvement essentially in the usability and functionality, essentially. I will talk about the new feature, and I guess that's kind of the most interesting thing people want to see, and probably also give you a general idea of the direction where we are going with geometry. Okay, so let's jump. In terms of improvement, there have been a lot of improvement behind the scene. Essentially, we rebuilt the whole, pretty much part of the whole framework in geometry to be able to accommodate a lot of requests from user and functionality. So to make, I kind of over-engineer it and make it ready to, to support more features. But one thing I would like to essentially talk about is what we did for Boolean operation. So most of the people want Boolean operation and quite useful for modeling and such. So what we try to do is to improve the Boolean operation in version. Well, that's strange. Sorry. To try to improve the Boolean operation in this coming version of right, that's translation. Well, so we improved the Boolean operation in version 12. And one of the key things we try to do essentially, or the key idea actually, which does apply to other functions in version 12, is that we try to preserve the type. So if you give us mesh region, we try to return you mesh region. If you give us formula region, we try to return you formula region. So we stay in that class of family. But that also means that some operations are not mathematically correct, right? So if you take a mesh region which is closed and you do a difference, you will probably get an open set, right? Where red mesh is already closed. So essentially, in that case, we could give you, the closure of that set. But we know that is what kind of user expect when you do modeling, when you manipulate a mesh region. But if you take an implicit region and then you do a difference, you probably get another implicit region where you can actually, which will probably open because you can actually represent things from those forms. So that's one of the key things we try to do behind the scenes. So I will just give you some basic examples. Plus, we have, which I'll probably talk later about polyhedron, which is a new basic primitive we're introducing. So we're also using it because it's one way to actually represent cells, basic cells, and it allows us to give computation. So in version 11, I believe, if you do that operation, we get a boundary mesh region. Right? But now you can get actually a polyhedron, a nice representation, you can actually manipulate it. So we continue to improve Boolean operations. And this kind of show you actually the improvement. I think this was region intersections. So our goal is actually to reach 100% in terms of benchmark. So this is a random set of, I think, 400 STL files. We downloaded and we try to see how good we are doing. From 70%, we are now at 95%, but we need to reach that 100%. Right? And Boolean operations are really complicated, actually. At first, it seems to be that easy. But we need behind the scene to be able to recognize the structure of the object you give to us. If they're line, we need to have algorithm for line-line intersection to have the right efficiency. Right? If they are polygon intersection, triangle intersection. But also we need to, if you give us exact input, we need to return you exact output. So we need to have those algorithms. If you give us approximate machine numbers, we need to return you machine numbers. So we need to build all that behind the scene. So that's probably one of the functions we'll keep improving every release. So we are kind of working hard on that. So what I'm asking is just patient, but we'll get there. So the next thing is essentially discretization. So in the coming version, actually, we improve our discretization for a nonlinear primitive. Spline, B-splines, tube and such will start to work now. So this is a basic example of a B-spline. You generate it, you can discretize it, and then you get a nice region there. So that also means, for example, exporting your file in STL will automatically work if you want to do 3D printing and such, because we can also kind of generate them. What also we hope in the future, like you probably noticed, our discretization currently doesn't handle multi-primitive. So if you take a bunch of spline with balls, you probably cannot combine them to return you a nice mesh region, because obviously that requires Boolean operation. So as soon as we have a better Boolean operation, more stable one, discretization also will improve, and discretized graphic. There have been also some improvement in discretized regions, and we hope that Boolean operation also will improve the discretized region in that same direction. We'll be able to discretize implicit region and give you sharp edges and all those nice features. So the next thing, which is slightly related, is cylindrical decomposition. I believe Adam can probably talk a little bit more about it later in his talk. Implicit region, essentially for several operations, rely on CAD, essentially. So what we can do here, essentially, we can, through cylindrical decomposition, give you the boundary of a set, the closure, the interior. So this is a basic inequality, polynomial inequality. You can ask the boundary, it will give you the boundary if you plot it. Or you can actually ask the connected component, you'll get it there. So it's what's actually behind the scene for implicit region when you give, polynomial equality or inequality form. And we hope that as we move forward, we are going to actually introduce more function, topological operation for geometry in general. So one other improvement, actually I put here, one other improvement is on our integral measure. So we introduced surface area, which was highly demanded because people wanted to compute the area of a ball, and we usually just come back and tell you that's not possible. So it was kind of half confusing. So we introduced surface area now, which actually does that and returns the right value. And it actually works pretty nice when possible. So here you have an intersection of two balls, and you can compute the surface area. Oops. My selection doesn't work correctly. Well, it takes some time, but you will compute the surface area and return you the exact value when it comes back. In this case, 5/12. Right. So also what we did is we added more support for assumption generate condition for those integral measures. Right. So in this case, for example, I can take this implicit region and ask the area, you return we have a, it's a non-constant region. It have a parameter A. You say generate condition, it will return you the conditional answer. Or you can give an assumption which is false. In this case, it will tell you, well, not per se false, but the region is infinite, for example. So you can do symbolic computation on top of our region pretty nicely now. So we support assumption and such. But also what we did is that we added working precision goal, and all the numeric operation, essentially to provide a new workflow. So what we notice in some cases is that if you give a, let's see, probably this will not work for this one, but if you give a complicated implicit region, let's suppose cosine, let me try to be adventurous here. So if you try to compute this, right, behind the scene, we try to first find the exact output. In most of the cases, you'll probably fail, right, because the expression gets really complicated. I mean, you can give any arbitrary implicit region. So what we try to do essentially to see is that can we have a numerical method to actually do that? Most of these are integral methods, so you can call probably, or reformulate it as a call to n integrate. So we can generate you a message and give you an approximate value. So that's kind of the idea about working precision goal behind. So in most of the cases, you'll be able to actually get an approximate value. And if you want an exact and you are ready to wait for 2 days, then you can just set those parameters. And we hope to propagate all those parameters throughout all the functions, geometric functions. Okay. One other requested feature was to actually support empty region, full region, mesh region, and boundary mesh region as graphic primitive. So we added it. Essentially, you can generate a mesh like that and use it in graphics. The graphic primitive, you can use opacity and all the stuff you want. So that gives you the flexibility, for example, to add texture, which we don't yet have for meshes. You can manipulate all that already. So other feature, actually, other improvements are on transform regions. So as I said before, we try to stay in the class when we do operations. So here you take a tetrahedron. You can give him a function, and then it can give you the result. So essentially, what we do behind the scene is that we look at your function. Like in this case, this is a linear function. This is a tetrahedron. It's a linear object. We know that the mapping will be always linear. And then we can actually analyze the structure, the function, and the object, and do the operation. And we do the same, roughly speaking, for mesh. We assume if you use mesh, that means you want to get at the end a mesh object, right? So in this case, a function which is nonlinear. We take it, we transform it to mesh, and try to actually find the right cell structure close enough to the output, and then we return you a mesh object at the end. So we try to remain in that class of mesh thing. Or you can do the same for implicit region. Down here, let me erase this output. So down here I have a mesh, an implicit region. I can compute the inverse quite easily, and I get the implicit region. Right. So we kind of mix the numeric, symbolic, and all the technical at once, but try to remain in the same class. So I kind of stop here because I can spend the whole day kind of talking about the improvement, which I've been working for a while. But essentially, we improved the selection of algorithms, so how we switch between the different algorithms you have and precision and exactness. We support multi-representation. So you give us a triangle, you give us a mesh region, we understand that they are roughly the same object, because you can represent a triangle as a mesh object. And then we pick the right algorithm to do the computation and return you a triangle at the end or a mesh region, depending on how you give the input. So we need to make all those decisions behind the scene. And also, we do a lot of canonicalization. So we detect basic error. Like if you take a cuboid, in our specification, you have to give the lower bound, the lowest point, and the higher point, the two corners. But most of the people, you can get confused and give the opposite. Right? Those are tiny errors we can correct. So we detect that, we readjust that automatically, and then everything works. As I say, support of assumption, generate conditions through the whole system. And obviously, performance improvement. We always try to be fast and give you the best result possible. And there is more. But anyway, this is kind of briefly what we have been doing. So let's see what's new. OK, I will start with angles. So what we did in version 12 is that we introduced PlanarAngle to compute angles. So you can compute counterclockwise or clockwise based on the specification. So P is your point, and Q1 and Q2 are the two endpoints. You can just use that, or you can use a string to say clockwise or counterclockwise. So you can pick the angle on both sides. And obviously, it works with symbolic value too, when possible, and generate condition and assumption too. And also one specification which was requested is in form of a triangle. Essentially, what's the interior angle for a triangle. You can say the interior angle, the exterior angle, or the full angle, right? Depending on which type of angle you want. So PlanarAngle is simple. You can generalize a PlanarAngle in two ways. In 3D, you can define it as a DihedralAngle between two planes. So here you give the 2 points, P1 and P2, and then the two vectors which define your planes. Or you can actually use explicitly our half plane to define it. And then you get, roughly speaking, the right angle. So we can also compute all that nicely. And it also supports symbolic values. The second generalization of PlanarAngle, of DihedralAngle, sorry. I will jump this example due to the time. The second generalization is solid angles. right? So essentially, solid angle is an angle at a point P spanned by a set of vector, or is an angle subtained by an object, roughly speaking. Right. So currently, we can actually compute solid angles of a vector, which is essentially, if you look at the 3D case, is essentially the measure of the surface area of the intersection of the cone from that point with the ball, the unit ball. Essentially that. So all these functionality are quite useful depending on what you are doing. So we have PlanarAngle, DihedralAngle, and SolidAngle. So pretty much all the generalization. And SolidAngle will in principle work in ND. Okay. I will just slightly talk about though. Just say that we introduced a synthetic geometry in 12, and I've been using a lot of the existing functionality. There will be a talk later on, actually, I believe at 3:30 about that. So you can stick around and look at that. So essentially, it's more a kind of theorem prover and generating an instance of theorem ascension and such. So, and as you see, it kind of rely on the new functionality about angles and such. They kind of need. Okay. Well, the key feature in 12 is polygon. Actually, that's not true, right? We have polygon since version, I don't know why. What we actually did in version 12 is that we introduced polygon with holes. Almost say angles, but polygon with holes. So before our polygon, essentially, you define them with a set of point or coordinate. So I have a set of coordinate there. You can get the polygon. Right? So I wrap it around region to rounder. So the first thing you notice is that we introduce a type setting for polygon. Right? And the type setting contains the number of points and the bound, and you can actually analyze it efficiently. So that's the easy part. That's what we had before. And one key thing to remember is that there are several definitions of polygon. Most of the people are not used to it. In our documentation, actually, that's the main line here, one line. We use essentially the recrossing intersection, the number of odd or even line of intersection, especially when your polygon have intersections, self-intersections. So now what we did in 12 is that we introduced polygon with holes. So you can also, quite similar to what we had before, give a set of points, and after that give a list of holes as a list of points. So in this case, I define that. I have my list of points, so that's kind of define the outer boundary, and that's the hole, the inner boundary, and then you get that there. And you can notice that this object I define is actually essentially the same I had before. Right? Here you define it by a set of line intersection to the recrossing. And as I said before, what we do behind the scene to do geometry is that we actually look at those representations. Even though they are different, we understand that they are the same. And we can do the computation and return you the correct answer. So there's all that framework behind the scene we kind of automate to actually analyze that. So that's one form of the polygon we extended, so you can use a rule to define it. Yes, please?
Why do you need the arrow, the rule to define the hole? Why is it just another argument?
Well, that was the simplest representation we found, and the easiest one to type. Right? It's more about outer boundary you associated to the inner boundary. So we went that way. Later on, Jebon will probably talk a little bit more about polygon, and we can probably discuss a little bit more about that representation. So the next representation we have is polygon, which is roughly similar to the graphic complex. You can give a set of points, and then the data. So these are the coordinates, and then you have a list there. So it's roughly that graphic complex you are used to representation. And this is quite useful for the next object I'm going to talk about, which is polyhedron. As you can imagine, polyhedron is a bunch of faces which are coming from polygons. So you don't want to duplicate points and such. So this representation of graphic, in that graphic complex form allow you to actually have a compact representation as such.
What happens if the inner polygon boundary is self-intersecting?
We handle it correctly. So there is no restriction. The outer polygon, the inner polygon can all be self-intersecting. We want depending on your definition, our default definition is the recrossing. Right? We do that correctly and appropriately. So it's all that complicating behind the scene. We need to actually be ambiguous and solve. No, essentially, so like in this case, right, you can have a self-crossing here and self-crossing there. So, in the simplest way, you just say what we do is that we canonicalize this. We find an outer boundary and inner boundary, and we do the same for all the holes, outer boundary, inner boundary, and then we do a difference, a region difference for them. But we need to do that efficiently, that if you gave us 10 million of them, we don't spend the whole day doing that. And JBOM will talk about in general about the canonicalization of polygons. So you can actually, if you have a function, canonical polygon, you type it and then it actually gives that form. You give the canonical form we use internally. Actually, we provide externally. So I will go really fast. We don't have much time. So there is a lot of function related to polygon. As I say, canonicalization, polygon coordinate, outer, inner polygon. You have crossing polygon, winding polygon, depending on the definition. People define sometimes the definition based on the winding number. So you gave us 2 polygons, we can figure that out. We have a new random generator for polygon, convex polygon, sample, and such. And also we can do decomposition polygon based on convex, sample, and such. So, okay, I will just continue really fast on this. So the next object we introduce is essentially, I'll also bypass the optimization. I think Yuzo talked earlier about all the improvement. The front end also did a lot of improvement to support polygon with holes, as well as be extremely fast in terms of rendering. So the next object we introduce is polyhedron. So it roughly have the same syntax as polygon, but now you have a list of coordinates. So this, a list of polygons. So this is an example. It also supports you can have void, you can have tunnel, and all the fancy things. So if you just have the whole idea of polygon in mind, polyhedron is kind of roughly the same generalization. And you can also specify it with holes with the same rule and such. So what we try to do is to maintain that same form and that same structure, so that's kind of natural to you to just manipulate it. So I'll just bypass all that, and with a couple of seconds I have, so our plan is essentially to keep improving geometry, mesh region, and functionality. Actually, we are going to do an additional functionality or request functionality for mesh region. And we hope to add new primitive or support of nonlinear primitive, spline and nub and so on. Polytop, support in n dimension, all those type of nice feature, and also do vertical and application. We did 3D printing, we do it game engine, virtual reality. More will be coming where we kind of show our functionality in geometry. And well, if you want to know more about Polygon and polyhedron and all the nice things we have, well, stick around. JBOM and Jan will talk right now about all that. And probably at around 3:30, there's also talk about planar geometry. Thank you.